Good evening to all of you. So today is our week 10 and we are going to start our this lecture, diagonalization. So in this chapter we will discuss some points as we discuss in a class. Are you present? Are you there, dear Imam and Abdul Rahman? Can you hear my voice and can you hear the PowerPoint slides? Can you see? Yes, okay. So uh, first of all, as we discussed in a class, that the diagonalization of a matrix A is a process. Diagonalization of a matrix A is a process of reducing A to a diagonal form. If A is related to D and by a similarity transformation such that D is equal to M inverse AM, then A is reduced to diagonal matrix through the model matrix. That is, we say model matrix MD is called a spectral matrix. And so reduction of a matrix to a diagonal form. How we can reduce of a matrix to a diagonal form. So as we discussed in a face-to-face class, there is a procedure to convert a matrix into a diagonal form. So there is a process. So a square matrix of A of order n has n linearly independent eigenvectors. Then a matrix B can be found such that B inverse AB is a diagonal matrix. So this is the definition of the matrix. Now the matrix B which diagonalizes A is called a model matrix of A, and which obtained by a grouping of eigenvectors A into n eigenvectors square matrix into n square matrix. So the symbols are a little bit different as we discussed in the face-to-face class. The symbols are different, and here PowerPoint slides the symbols are a little bit different because of I'm unable to find the similar PowerPoint slides. So that is why it is a little bit different. So this is called the model of the matrix. So next is similarity of the matrix. A square matrix B of order n is said to be similar to a square matrix A of order n if B is equal to M cross M. That is the same thing that we going to discuss. So this is the diagonal matrix for some non-triangular matrix. So this transformation of the matrix A by non-singular matrix MB is called a similar transformation. Note, if the matrix B is similar to matrix A, then B has the same eigenvalue as A. So these are some definitions, some properties. So for example, let us discuss a question. With the help of this question, we can understand easily what we want to say about this. For example, reduce a matrix A, and this is a matrix, to a diagonal form by similarity transformation. So this is the question, and we will not discuss this A cube. So we are only discuss up to here. So reduce the following reduce the matrix A to diagonal form by similarity transformation. So we know that first of all, what we have to done, we know in a face-to-face class, I told you that we have to write a matrix like P inverse and A into P. We have to write like this. So first of all, we have to write, we have to find the P. We have to find the P. So for P means we have to find the eigenvectors. So eigenvectors, yani P1, P2, and P2 and P3. Whatever the eigenvalues corresponding to their eigenvalues, we have to find the eigenvectors. So we have to start. So we are going to start to find the eigenvalues. So eigenvalue, we know the formula to find the eigenvalue. First of all, we are going to start find the characteristic equation. Yani the formula of characteristic equation is minus lambda I minus a is equal to 0. This is the equation of the characteristic equation. So lambda I minus a is, this is the equation of characteristic equation. And when you are going to solve this determinant, so when you just cross multiply it, and small, and we know how we can open this determinant. So when you are going to open the determinant, there is a cubic equation, and when you are going to solve this cubic equation, there are three values of lambda. So lambda is equal to 1, 2, 3. There are three roots of lambda. So this is called the eigenvalue. The root of this characteristic equation are called the eigenvalue. Hence, eigenvalues of A are 1, 2, 3. Now, what is our aim is to find P1, P2, P3. So, what is P1? P1 is the eigenvector corresponding to the eigenvalue 1. Similarly, find the eigenvector corresponding to the eigenvalue 3. To similarly find the eigenvalue corresponding to eigenvector 3. So wait a minute. So as we discussed, these are the eigenvalues. Eigenvalues of A are 1, 2, 3. So now our aim is to find the eigenvectors corresponding to eigenvalue 1. So we move further. So we have to find eigenvalue lambda is equal to 1. First of all, we will find step number 1. We will find the eigenvector corresponding to lambda is equal to 1. So there is a formula to find the eigenvector. So the formula to find the eigenvector is lambda I minus a, or bracket x is equal to 0. This is the formula to find the eigenvector. So with this formula, we use the eigenvector, put the value of lambda is equal to 1. Here we put the value of lambda is equal to 1. So we find this matrix and multiply this, and we will get three equations: equation 1, equation 2, and equation 3. We get and solving these equations, three equations, 3 unknown, and solving these equations, we get this. So we have this. This is the eigenvector. 1, 0, 0 is the eigenvector corresponding to lambda is equal to 1. Now next, similarly, we have to find the eigenvector corresponding to lambda is equal to lambda is equal to 2. So our next aim is to find the eigenvector corresponding to lambda is equal to 2. So in the same matter, same process again we have to repeat. We know the formula of eigenvector corresponding to lambda. The formula of eigenvector is lambda I minus a lambda I minus a into x is equal to 0. This is the formula to find the eigenvectors corresponding to lambda. So put the value of lambda here as 2. So when you are going to put the value lambda is equal to 2, you will get minus 1, and so similarly we will get these equations, and we get this matrix. So this is the matrix we obtain by putting lambda is equal to 2 and solve them. And when we are going to solve, we get three equations: lambda equation 1, equation 2, sorry, equation 1, equation 2, equation 3, and equation 3. So when you are going to solve, there are some equations. So from here we get that again eigenvector. This is a eigenvector. So now lastly, on the last term, we are going to find the eigenvalue corresponding to lambda is equal to 3. We have to find the eigenvalue corresponding to lambda is equal to 3. So similarly, again, we know the formula of eigenvector. This is the formula of eigenvector. Now put the value of lambda is equal to 3 here. We obtain this matrix. So when you are solving this matrix, we are again the three equations. We are again the three equations. Here we obtain only two equations because of two equations are same. That is why we obtain. So equation number 1, here we obtain equation number 1, and equation number, why we obtain only two equations? Because as we observe that the third row is total 0. That is why we obtain, it is a 2 by 2 matrix. That is why we obtain only two equations. So we obtain only two equations, equation number 1, equation number 2. So corresponding to these two equations, we obtain the eigenvector. This is the eigenvector 3 minus 2 minus 2. So till now we find P1 and P2 and P3. So till now we find the yani P is equal to P1, P2, P3. Till now yani P1 is the eigenvector corresponding to lambda is equal to 1, P2 is the eigenvector corresponding to lambda is equal to 2, and P3 is the eigenvector corresponding to lambda is equal to 3. Now combined all these three P. So when we are going to combine all these three P, so there is a matrix. We form a matrix P1, P2, P3, and that matrix is called a P. So let's see in a next slide. Let us see. So this is the P final. This is the P that we form. This is the P that we form. The combination of the eigenvector. This is P1 and this is P2 and this is P3. So this is the combination of the eigenvectors. So this is P. Now to find the inverse. So there are several methods to find the inverse. Here they use this method, adjoint method. This is the formula to find the inverse. So there are so many methods, either row reduction method, and there are so many methods. Here we use the adjoint method. Now M inverse AM is equal to this. This is the diagonal matrix. This is from the diagonal. This is diagonalized. This is, so 1, 2, 3 is diagonalize the matrix. So this is the procedure to solve to diagonalize any matrix. So one problem I discussed in a class. Now this is the second problem, and it is no need. There is no need to see. Next is orthogonal transformation of a symmetric matrix to diagonal form. A square matrix A with real elements is said to be orthogonal if A transpose is equal to I, and I into I, A transpose is equal to I. But A into A inverse is equal to I, A inverse into A is equal to A. It follows that A is orthogonal if A dash is equal to A inverse. Diagonalization by orthogonal transformation is possible only for a real symmetric matrix. If a real symmetric matrix, then eigenvectors of A will not only be linearly independent but also pairwise orthogonal. If we normalize each eigenvector and use them to form the normalized model matrix N, then it can be proved that N is an orthogonal matrix. The similarity transformation, this is M cross M inverse AM is equal to D, takes the form it is M dash A N, since N dash is equal to N dash by property of orthogonal matrix. Transforming A into D by means of transformation N dash A N D is called the orthogonal reduction or orthogonal transformation. So to normalize eigenvector XR, divide each elements of XR by square roots of the sum of the square matrix. So these are some definitions that we discussed earlier. It is just you understand. So there are some one more example of that. So from this example you can understand more clearly. So the question is, diagonalize a matrix A by means of orthogonal transformation. So similarly, first of all, we have to find the eigenvalue. To find the eigenvalue, we have to we are going to start first of all. We have to find the eigenvector. So the formula of to find the first of all we have to write the characteristic equation. So the formula of characteristic equation is lambda I minus A is equal to 0. So this is the lambda I minus A is equal to 0. This is the characteristic equation. So here we write the characteristic equation and solve this determinant. So there is a 3 by 3 determinant. So there is a cubic equation. So we form a cubic equation, and lambda cube minus something is equal to 0. So there are 3 roots are there. So this is a cubic equation. And when you are going to solve, there are 3 roots. Lambda is equal to -1, lambda is equal to -2, lambda is equal to 6, lambda is equal to 6. So the roots of the characteristic equation are this -2, 6, 6. So it is called the eigenvalues. So what you say? There is a cutting. What cutting? There is a cutting. There is it. It is cutting. What Farhad? Fahad? What do you say? Okay, no problem. So next we move. Similarly, we find the eigenvector corresponding to these all 3. So the eigenvector corresponding to lambda is equal to -2. So again, there is a formula to find the eigenvector. The formula to find the eigenvector is lambda I minus A into x is equal to 0. This is the formula to find the eigenvector. So put the value of lambda is equal to 2 over here. Then you get this matrix and multiply this matrix. So we obtain 3 equations: equation number 1, equation number 2, and equation number 3. Solve these 3 equations, we get the eigenvector. So this is an eigenvector. Similarly, to find the eigenvector corresponding to lambda is equal to next lambda. Lambda is equal to 6. So again, we are going to repeat this process again. So this is the formula of eigenvector. To find the eigenvector, lambda I minus A is equal to 6. The value of lambda here is 6. So in this PowerPoint slide, I observed that they write A minus lambda I. A minus lambda I. But you don't confuse with this, because of in lambda I minus x is equal to 0, where you don't confuse with this, because of I discuss I discuss in my face-to-face class like this: lambda I minus a is equal to 0. So both the things are same, just multiply minus sign, the result is same, both are same. But in this PowerPoint slides, they use a minus lambda I. Both are equal, no problem. So uh, so they form the matrix a minus lambda I, a minus 6i is equal to 0. So there is a matrix, and x1 is equal to x2 is equal to is an arbitrary matrix. Uh, so x2 is x1 is equal to x3, and x2 is an arbitrary. So x2 must be chosen that x2 and x3 are orthogonal among themselves, and also each of the orthogonal with x3. So there are three eigenvectors we choose. So model matrix. So with the help of same, the problem is same. You will see it. Again, we can form the model matrix. Now there is some normalized model matrix. There is some more extra question how we can normalize the model matrix. So to normalize the model matrix, we have to divide under root 2. We have to divide under root 2, then it will become the normalizer matrix. So this is the diagonal matrix that we form. This is the procedure uh, to draw a diagonal matrix. So next is quadratic form. Next topic is quadratic form. A homogeneous polynomial of second degree in any number of variables is called a quadratic form. So if we have ax square plus 2hx plus by square, it is a quadratic form. So with this, how we can draw and the matrix. In a few slides, after 2 or 3 slides, I will show you how we can draw the matrix from this. And there is a equation, quadratic equation, one equation quadratic, and there is this equation, equation number 3. So are quadratic forms in 2, 3 or 4 variables. Now the question is how we can draw the matrix with the help of these quadratic forms. So let us see. First equation is ax square plus by square plus cz square plus 2hxy plus 2gx 2fzx. So first we write xyz over here, xyz here, and ABC. First we choose the ABC, whatever the coefficient of the x square y square. So we took the coefficient a square y square a square y square z square in the diagonal form. We put all the elements in the diagonal. Then we are going to start whatever the value of hxy to hxy, gxy, fzy. So this is the value of 2hxy. So what is here is written is h. So we can write our main equation is 2xy. Here 2 is already written, so we write h over here. And similarly, if I write h here, then h is again here. It is a similarity. Then we are going to write 2gx. So 2 already written, so only we write g. We write g here. So that is a because of g is similar, so g is also here. So in this way we can write, and lastly f is remain, so f I write over here. So in this way we can write the matrix like this. We can draw the matrix with the quadratic form. So similarly, the another quadratic form is written ax square plus by square plus cz square So first of all, we write the matrix. First of all, we write all the elements in the diagonal A, B, C, D. Whatever the elements of the square, any A square, B square, C square, and uh, D. It is D square. It is DZ square, right? Not 2 DW2. It is written wrong. It is a square. So we write all the elements in a diagonal form. Then we have to start H to HXY. So we write H over here, H, then move further to similar. It is similar to GX. Then we move G here and G here, and it is similar. So I write here, and H is similar to I write here is here. Then move F, so F here, and it is similar, so that's why it's here. And again I write L, so I write L here and L here. Similarly M and N. So totally I can draw the whole matrix over here. So in a book it is defined clearly how we can write the matrix, but in PowerPoint slide is not shown clearly. So, but in I think in my face-to-face class I show you the exact method to draw the how we can draw the matrix. But hope you can understand how we can draw from this to the matrix. So let's move. Nature of the quadratic form. So there are few types of quadratic forms. A real quadratic form x dash ax in n variables is said to be real. There are 5 points. First, it is said to be positive definite if all the eigenvalues of A are positive. A is greater than 0. It is said to be negative negative definite. The third point is it is said to be positive semi-definite if all the values if all the eigenvalues of A are greater than or equal to 0 and at least one of the eigenvalues is 0. Fourth point is negative semi-definite if all the eigenvalues of A is less than 0, less than or equal to 0, and at least one of the eigenvalue is 0. Indefinite if some of the eigenvalues of A are positive and other are negative. So there are 5 points we discussed: positive definite, negative definite, semi-definite, semi-negative, and indefinite. So there are 5 points from which we know that what is the nature of the, from that we can know that what is the nature of the quadratic form. So there are some questions. In this question you have to ask that find the nature, tell us the nature of the quadratic form. What is the nature of the quadratic form? So let us see the questions. So this is the question. First, in a main exam, maybe you have to given like this: a equation is given, and you have to ask them what is the nature of the quadratic equation. This is to find the nature of the following quadratic forms. So first of all, you have to write it into the matrix form. So we know how we can write the matrix form. First of all, we write the coefficient of x square, y square, z square. So we write the coefficient of x square is 1, coefficient of y square is 5, coefficient of z square is 1. We write the diagonal form. Then we move to next, yani xy, yz, zx. So we move 2xy. So what is the coefficient of 2xy? What is the coefficient? Is 2, because of our standard form is 2xy, 2yz, 2xy, 2 plus 2yz, 2zx, whatever this is our standard form. So 2 is already present here. So the coefficient of xy is 1. So that's why I write 1 here and 1 is also here. Similarly, I move yz, the coefficient of yz over here, similarly yz, coefficient of yz here, and the coefficient of zx is 6. So our standard form is 2zx. This is our standard form, but here it is written as 6zx. So what is the value actually? So the value of what is the value here? The value of here is 2 3, or we can write 2 multiplied by 3. So zx we can write like this. So it means there is a value, 3 is the value. So that is why we write 3 here and 3 here. So this is the matrix. Yes, you are right, Fahad. So this is the we first write in the matrix form. Now the question is, what is the nature of the quadratic form? So to find the nature, we have to find the eigenvalues. And to find the eigenvalues, first, from where we start? We have to start write a characteristic equation. Lambda I minus a is equal to 0. We have to write this characteristic equation, and from this characteristic equation we can obtain the eigenvalue. So let's see. So directly he solve it. You will try at your home, but directly he will solve it. The eigenvalue of this matrix is minus 2, 3, 6. So these are the eigenvalues. Yani lambda is equal to minus 2, 3, and 6. So these are the eigenvalues. So which kind is it? There are some a negative eigenvalue and some positive eigenvalue. So what is the nature of the quadratic form? So let us see in previous slides. So let us see where this is. Where is no where? So it moved directly. Wait a minute. So if we see here, this it is automatic move. So in this page, oh no, it is moved. Okay, leave it. So we are going. What happens? So this is the quadratic. So we observe from previous page that some values are negative and some values are positive. Yes, it is indefinite type. Yes, you are right. That two of these eigenvalues are being positive and one being negative. So the given quadratic form is indefinite. So similarly, the second question. 3x square plus 5y square plus 3z square minus 2yz 2zx plus minus 2xy. This is the equation. So find the nature of this quadratic equation. So first of all, we have to write a matrix. So we are going to write a matrix. So again, we draw the diagonal form. First we write the diagonal element 3, 5, 3. Let's see what are the diagonal element in the previous slide. The diagonal element are 3, 5, and 3, and rest of the element are here minus 1, 1, and minus 1. So these are the rest of the elements. So this is a so the eigenvalues of A are 2, 3, 6. So all these eigenvalues being positive, so the given quadratic form is positive definite. So yes, yes, you are right. Positive, yeah, it means it is a quadratic form or positive definite. So this is approximately end of the lecture. Till now it is all the all the things we discussed, but there are some few slides I added. So there is a kind of revision. I will discuss it again. So I'm going to revise what we discussed till now. So first I discussed the diagonalization of the problem. So this is, we can write like this: P inverse AP. In this slide it is written as P inverse, but in previous slides, they use D inverse and D. So no problem, whatever the notations, but we have to understand the basic concept. So a square matrix A is called the diagonalizable if there exists an invertible matrix P inverse AP, a diagonal matrix P diagonalize A. So if there exists an invertible matrix P such that B is equal to P inverse AP, the eigenvalue of the eigenvalue problem is related to closely to the diagonalization problem. So there are some similar matrix. Uh, diagonalize a matrix. There is a question is given, is written, diagonalize a matrix. Diagonalize a matrix. Yes, there is a problem. But the slides are going on. I don't know what's going on. So let's see. The diagonalize this matrix. So as you know that to diagonalize, first of all we have to find the characteristic equation. So this is the characteristic equation: lambda I minus a is equal to 0. So this is the actual. In this slide they use the same our as method that we discussed in the face-to-face class. With the same method they use lambda I minus a. So we use the characteristic equation and we form this equation, and there are three roots: lambda 1, lambda 2, lambda minus 2. This is called the eigenvalues. And now to find the eigenvectors, so one by one first they found the eigenvector corresponding to lambda is equal to 4. So eigenvector corresponding to lambda is equal to 4 is 1, 1, 0. Similarly, now move to eigenvector corresponding to lambda 2 is equal to minus 2. So with this they form 1 1 1 minus 1 0 and 0 0 1 directly. And to make the main P1 P2 3 combined all three eigenvectors, they form this matrix, and combine P inverse AP is equal to this. So this is a diagonalization of the matrix. That is called the diagonalization of the. Or we can write, so it shows that either, or we can write like this, yani P2 P1 P3 both are the same thing, no problem. If you write P2 first, P3 second, and P1, so both are the same thing, there is no any problem. Either you write here or write here, there is no any problem. So there are some conditions. If n cross n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. So there are some definitions. So some more examples are written. You will see diagonalization of the matrix lambda is equal to, same examples are there. You will see at your home. You will check and practice it. Sufficient condition for the diagonalization: if an n cross n matrix A has an n distinct eigenvalues, then the corresponding eigenvectors are linearly independent, and A is diagonalizable. Determine whether a matrix is diagonalizable or not. So we see a matrix because A is a triangular matrix, upper triangular matrix. So the eigenvalues of the main diagonal. So lambda is equal to 1, 0, and lambda 3 are the eigenvalues directly. These three values are distinct, so A is diagonalizable. So by the theorem 7.6, it says that. So find the diagonalizing matrix by a linear transformation. There is some other way, but there is no need. So next thing is symmetric matrix or orthogonal matrix. So it says that a square matrix A is symmetric if it is equal to its transpose. A is equal to A transpose, then it is called a symmetric matrix. A is equal to A transpose. For example, there are some few examples of the symmetric matrix. Whether it is a symmetric matrix or question is symmetric matrix and non-symmetric matrix. So A is symmetric or not. So let us see. There is a diagonal element. 0, 3, 5 is a diagonal element, and rest of the 1 is here on the right side. So 1 is here on the left side, and minus 2 here and the right side, minus 2 here is the left side, and 0 here on the right side, 0 here on the left side. So yes, it is a symmetric matrix, we say that. And similarly, if we say it is a 2 by 2 matrix and there is a diagonal element, and if we say there is 3 right side and 3 is left side, so it is a symmetric matrix. So in a 3 by 3 matrix, this is the diagonal element, and if we are going to see the here right side is 2 and left side is 1, so it is a non-symmetric matrix. Now move further. Eigenvalues of matrix. If A is an n cross n symmetric matrix, then the following properties are true. A is diagonalizable. We can diagonalize a symmetric matrix. All the eigenvalues of A are real. And the third property is if lambda is an eigenvalue of A with multiplicity k, then lambda has a k linearly independent eigenvectors, that is, the eigenspace of lambda has dimension k. So a square matrix P is called orthogonal if it is orthogonal, if it is invertible, and P transpose is P inverse is equal to P transpose. So example, if P is equal to 0, 1, minus 1, 0 is orthogonal because P inverse is equal to P transpose. If we are going to, yani P transpose is equal to P. So P inverse is equal to P transpose is equal to 1, 0, 0 minus 1, 1, 0. Similarly, if there is another matrix and is orthogonal because P inverse is equal to P transpose. So it is an orthogonal matrix. Properties of an orthogonal matrix. and n cross n and matrix P is orthogonal if and only if its column vectors form the orthogonal set. So there is some example. An orthogonal matrix is given. P is If P is an orthogonal matrix, then it must be true. P inverse is equal to P transpose, or we can write P into P transpose is equal to I. This can be done. So we have to show that whether if it is equal to I, if we show that P into P transpose is equal to I, then we directly say that it is an orthogonal matrix. So let's first we first we write the matrix A P, and secondly we write the transpose of the matrix P transpose. Here it is a P transpose of the matrix. So here it is a row and it will become column, and it is first row become first column. So similarly second row becomes second column and third row becomes third column. This is the way. So second row become second column. Third row become third column. And you are going to multiply these things and you will get the same. You will get identity matrix. So it means that P is an orthogonal matrix. So let P1 is equal to something, P2 is equal to this, P3 is equal to this, and there is no need orthogonal set, no need. Properties of the symmetric matrix. Let A be an n cross n symmetric matrix if lambda1 and lambda2 are distinct eigenvalues of A and their corresponding eigenvectors x1, x2 are orthogonal. So eigenvector, so show that any two eigenvectors of A corresponding to distinct eigenvalues are orthogonal. So we know how we can find the eigenvectors corresponding to this matrix. So there is a characteristic equation here, and we find the root eigenvalues are lambda is equal to 2 and lambda is equal to 4. Corresponding to lambda is equal to 2, find the eigenvector. So corresponding to lambda is equal to 2, the eigenvector is -1 and 1. Corresponding to lambda is equal to 4, the eigenvector is 1 and 1. So these are two orthogonal matrix. So there are some definitions. Determine whether the matrix is orthogonally diagonalizable or not. So if it is a symmetric matrix, then we say it is a diagonalizable. If it is not symmetric, then we say it is not diagonalizable. So it is, so you will see at your home whether it is just example. You will see orthogonal matrix, and the last topic is symmetric, skew-symmetric. There are some definitions of skew-symmetric. A real square matrix is called a symmetric if transposition leaves it unchanged. Any A transpose is equal to A, then it is called the symmetric matrix. If it is called a skew-symmetric matrix if A transpose A is equal to -A, and it is called the orthogonal matrix. And then A transpose A is equal to A inverse. There are some definitions. And lastly, a real matrix. A real matrix A is called a Hermitian matrix. It's called Hermitian. Lastly, Hermitian is co-Hermitian and unity matrix. A square matrix A is called a Hermitian if A into A bar A transpose is equal to A, and it is called a skew Hermitian if A transpose A star is equal to A transpose. Okay, but there are some problem I think in my laptop. So it is the end of the lecture. So you have any question? You will see these PowerPoint slides. Uh, you will see the I upload these PowerPoint slides on the Blackboard. You can see over here. So any question?